Hello guys, we are Team Amigos and this is our social network analysis project description video. There were 3 round submissions in our project and we took 2 datasets for our project purpose. The first dataset is the Texas road network graph. This dataset contains information about the road network of Texas, in which the nodes represent the intersections or endpoints and the edges represent the roads connecting these endpoints. The format of this dataset is that it is undirected and also it is unweighted. Although the original dataset was huge, but we sampled out and we took only 9125 connections or edges in our sample. Similarly, the second dataset is the Google Hyperlinks dataset. This is a network of web pages connected by hyperlinks. So in this dataset, the nodes represent the web pages and the edges represent the hyperlinks from one web page to another. So you can predict that this is a directed dataset, and so it is. And also it is unweighted. Now, like the previous dataset is also huge, so we sampled out and we took only 9485 edges or hyperlinks in our case.
Hello sir, I am Amit Judha and I will present a part of the first round in our project. So the objective is to work out all centrality measures, clustering coefficients and transitivity that we study in the class using appropriate algorithms on the chosen dataset. So the chosen dataset here is the Texas road network, where the edges are the roads in the network and the nodes is the intersection between those roads. So firstly, we apply degree centrality. Here's the graph for that. So it shows that the centrality value is very low for majority of the network, which is practical as well because we know that too many roads cannot intersect at a similar point. It's usually the number stays below 4 or 6. So that's how it's observed as well. Now we've used CAD centrality. Here it doesn't just account for the neighboring nodes, but also for the neighboring nodes of the adjacent nodes. So here we see that the graph has more of the similar like the last time only, but we also know that the centrality value has, so most of the edges have same number of nodes connected to them and further connected to their adjacent nodes. Now for the closeness centrality, we may observe that some of the nodes are really far from each other. So there must be nodes and edges at the corners of the network. And most of the network have a similar centrality value ranging from 0.015 to 0.030. So the roads are not extremely diverse in their closeness measure. Now for the betweenness centrality, a vast majority of the nodes does not belong to the shortest path, and that's practical as well because we don't have a particular intersection which will be very popular in a road network, and because the target of road network is to create closeness and not betweenness. But still we see that there are some net nodes, there are some intersections which have very high value for betweenness as well. So these are the important intersections. Now for the transitivity, we see that if a triad is made, then if and A is connected to B and B is connected to the C, then here we will see that the transitivity is very low, so the A will not be connected to the C, and that is very practical as well because if the two roads are already connected, then we don't connect the third part as well. So the global clustering coefficient is 0.03, while the local clustering coefficient, the graph is made here. So now we measure degree centrality, betweenness centrality, closeness and CAD centrality, and we found the global clustering value as well, which is very low. Betweenness centrality is very low as well, degree is very low as well, and closeness and CAD centrality are a bit better to observe this dataset. So the inferences here is that we've known about the intersections in the Texas city. We know the most vital intersections, like there could be facilities like security, traffic management, and road safety features. So all these features should be provided to the important intersections and not all the intersections. And how would we find those intersections would be because of their betweenness centrality and closeness centrality. So if a node's closeness centrality is very high, then we can use it for transport or trade purposes because it's very close to other intersections. And from betweenness centrality, we know that which roads will need high maintenance because they will be used very much, and security and other facilities as well. Low transitivity means that I've already told that if A is connected to B and A is connected to C, then we don't want B and C to be connected, and that's how Texas road network is. Thank you.
Hi, I am Akshit Agarwal and I'll explain how various centrality measures were carried out in the Google hyperlink dataset. So this is how our web page's hyperlink network looks like. We have used digraph here for plotting the directed graphs. So firstly, we have calculated degree centrality and we can see that more than 3000 nodes have centrality value around 0 and only few of the nodes have value around 0.006. So that means that most of the nodes have very few connection or reference to other web pages. So next we have calculated eigenvector centrality and we see that near around 4000 nodes have centrality value around 0 and only few a minute of them have values more than 0.20. And then we have calculated PageRank centrality and we can see that the values are coming quite better than the other above discussed centralities, and also we can see that the PageRank is more significant for the directed graphs. And lastly we have calculated reciprocity and its values coming near around 0.4. From this network measures, we have studied degree centrality, eigenvector centrality, PageRank centrality, and reciprocity. And for the graphs like ours, the directed graphs, PageRank is most significant. The reason is that PageRank takes link direction and weight into account, and also it passes different amount of influence to different web pages. So, degree centrality, we have seen that many web pages have its value around 0 only, and similarly for the eigenvector. And the normalized web page values are very useful in ranking the web pages on searches. And lastly we have calculated a reciprocity and its value was coming around 0.4. So the significance of our analysis is to study the most referenced web pages, and this is significant because whenever we search a web page on any search engine, the results the sorting of the results depend upon the page rank value only. So higher the page rank value, the on the top the results will appear. And also we have seen that most of the web pages are not getting the reference from other web pages. That is why the values of centrality for most of the nodes was coming around 0. And lastly we have seen that the reciprocity value was coming around 0.4. What it means is that around 40% of the web pages are mutually linked. That means that if there is any hyperlink from web page A to web page B, then there is also a hyperlink from web page B to web page A.
This is the second phase of our project. In this round, the objective was to find the maximum connected component for a given graph G, which is also called as the giant component. After that, we were supposed to plot the famous NG by N versus average degree graph. So for finding the giant component, we first plotted a random graph with number of nodes as 500 and with probability of edge creation of 0.002. So using the inbuilt Tortoise-Renai graph model present in Networks package, and by passing the two parameters 500 and 0.002, we got the following random graph. Now the next step was to find the number of connected components present. So we got that using the inbuilt function, and the answer was 295. So that means that there are 295 connected components present in this random graph. Now now the storing all these connected components in a list and printing them, we get this. So this is nothing but list of sets of connected components. So suppose if we pick this set of 226 and 86, so that means this is a connected component of size 2 with nodes as 226 and 86 namely. So similarly, there will be one such set which will be having the maximum size, and we will call it as the giant component. So next step is finding the giant component, and we start by finding the set with the maximum size. So that is a simple code over here, and we get the size as 27, implying that the giant component has size 27, and the corresponding set is as follows: this one of size 27. So the first part is done. Now next part was plotting the NG by N versus average degree graph. So for that we stored the ng by n values in a dictionary, and then to check the ng by n values we printed it, and as you can see it starts from 0.002 and goes all the way up to 0.988. Now since our ng by n values are already in a dictionary, next thing is plotting the ng by n ratio with respect to average degree by taking average degree as x-axis and the ratio ng by n as y-axis. So there's a simple scatter plot, and using the inbuilt function we get the following plot. So what you can observe about this graph, so we can observe that from as the average degree value increases from 0 to 1, then the increase is not so much, but from 1 to 4 the increase is exponential, and as the average degree value goes from 4 to 5, the value of ng by n saturates to approximately 1. So what we can infer from this, as average degree increases, so does the ng by n ratio, implying that number of nodes in the giant component increases with respect to average degree. This is because keeping n fixed, as average degree increases, so does the probability of edge creation, since we know that average degree t is equal to p times n minus 1 for our number. With increase in probability of edge creation, it is expected that more number of nodes will form edges with more number of connected components. And also, as ng by n tends to 1, we can say that the giant component in this case contains almost all the nodes, which is all good. Then decrease in the ng by n ratio at some points is expected, as although the p value increases, it becomes the rare case when with probability 1 minus p node tends to remain disconnected.
Further to the third round of project, here we are using the same data set as we utilized in a first round and second round, which was based on road networks of Texas. So here the roads here are edges, and the interconnectivity of those roads form a city or sort of node. So here you can consider those nodes and edges as an analogy to people and their connectivity between each other. So here we are trying to find out how these different nodes form a community, and how they are being distributed into different communities. So the one of the method is being using a brute force method, but as we know that brute force method will be taking a lot of time to find communities and found different groups. So the two different algorithms which we are using to enhance the speed and enhance the utilization are CPM and Girvan-Newman algorithm. So as here in the first part we have imported all those libraries which are required. Moving further, you can see the graph. So here we have done some pre-processing on our data set, and we have utilized 1000 nodes here, and the reason is because we have also tested the connectivity in 200, 300, 800 and above 1000 as 3000, 5000 and 8000. In less number of nodes the connectivity was quite not clear, and in large number of nodes you can see that this connectivity was quite dense, because of which we were not able to see how these nodes are connected with each other. So the best outcome which we could found out was 1000, and we have also done taken a condition here that each node must be connected to another node, because a single node does not form any community on its own. So to form a community we need sort of interconnectivity between different nodes. So here's the condition, and we have also excluded that case that any node is connected to itself. So we know that the connectivity between a person to a person himself does not form a community. So here you can see that this is reflecting some sort of outcome, but we need to know that how these communities are distributed in particularly. So first we are coming to Girvan-Newman algorithm. So this Girvan-Newman algorithm is mainly based on edge betweenness and how these edge forms interconnectivity between each other, and those edge which are in between or which constitute in many different findings shortest path are given a higher value on the basis of it. So in Girvan-Newman, as we have told that betweenness of a community is vital. So here we are finding how these edges constitute in finding the betweenness of each other, and then we are giving them a weight on the basis of how many times they value in shortest path between two any different nodes. So on basis of it we have given them weight, and then we have constituted the graph. So the one thing which was quite fascinating here is that first of all, the two different communities have been formed, and one of the inferences of us is that uh, no or none other sort of node is being left, because each node is connected to either the outer community or either the inner community. And this was one of the reason of finding a community, because any node must not be left alone in a community. So this outcome is being fulfilled, which was the main reason of our community. And then moving further with our another algorithm, which is CPM algorithm. So CPM algorithm is mainly finding critical path method algorithm, and it utilizes the shortest path to find different communities. So and we give different weights on the basis of how many times they constitute in the valuation of shortest path of a graph. So moving further with it, that the main aim was revolving around the fact that we need to find different clicks, because click are a condensed form of a small or a larger group. And if we are able to find, or if we are able to locate a click, so we can do a traversal from that particular place in that first order to find the other nodes which are a part of that community, and we can restrict our depth first length traversal to a limit. And then we can find out that okay, up to 5 people we know that these are part of a community. And if there's another click where the people is near to 5, then we can say that that particular person is a major part of that particular community. So here we can see by the graphs of the result that they are nearly the same as a given Newman algorithm, that the inner part is quite condensed and outer part is being also forming a community. And here we can see that these triangles are a reflection of click, and around each triangle you can notice that there is a formation of a community, which was our initial observation, which was our initial prediction that it would happen. And you can see in three different graphs which we have tried to show. And in each of these graphs the result is that in each of the graph there's a condensed community in the center, as you can see here, and there's an outer community, but the formation of this outer community is different. And the reason is because we have taken different initial nodes, and then we have taken doing the depth first traversal so to form a community. So if we are taking a different node for one sort of traversal, and then finding okay, this particular node is near to this community, so in all those sort of traversal we can notice one particular thing which was common, that the inner community was quite condensed and it was a part of it, although the outer community was being dispersed, but it was also revolving around the click, and how much near it is to the other click. And the distribution of the two communities was nearly, or you can see quite close to everyone, that only two forms are formed, and outer one is quite much away from the inner one. This is one of our conclusion, that the communities have been recognized quite clearly here. And the other outcome which we notice is that for a smaller data set we can see that utilizing CPM algorithms give us a clear result that how these members are part of one another community, and we can see a quite clear view of things. Thank you.